Okay, I want to do some examples of what closure is, or closed sets, interior points, open sets, and stuff like that. Complements. So we're going to talk about Kurotowski's closure complement problem. We won't solve it, but we'll just explore it a little bit. So this asks if I have a set of numbers on the real line. Say I have the closed interval from 0 to 1, and maybe I've got the number 2, and I've got, say, between 3 and 4, I've got some numbers. I don't take 4, but I take from 4 to 5. And let's not take all of the numbers between 0 and 1. Let's just take the rationals. So our set is all of these guys, this number, this interval here, this interval here. Okay. Let's call this set A. What are the limit points of A? Well, the limit point, we had to take any point that no matter which circle we draw around it, that point contains things from A. So let's see if we can draw in these limit points here. Let's use blue. The limit points, well, 2's not a limit point because it's isolated. Okay, so I don't have to have that, but every point in this interval is definitely a limit point, right? Those are the rational numbers. Those were the rationals. This is Q intersect 0, 1. We said that the rationals were dense, so any number I draw in here, if I draw a circle around it, that's going to intersect some of those. I also get all of these things here, including 4, right? So those are all the limit points. The limit points are anything between 0 and 1, union, sort of including things from 3 to 5 as well. Okay, so those are the limit points. The closure of a set is the smallest set containing the original set, which is closed. Smallest closed set, maybe I say it that way, containing the original set. Okay, so this is A union the limit points of A. We'll call this A prime is a closure. Sets limit points. The closure of the set. Okay. So a closure in this case, it's going to be the set and its limit points. I get 0, 1, union that point at 2. It's not a limit point, but it's originally an A. And then I get 3 to 5. Okay. So A closure gives me that stuff. Great. The complement of A, what's A complement? Let's go back to it white. Well, let's look at A again. Let's do the complement in pink. A complement is everything that's not in A. So I've got a bunch of points in here, the irrational points. I've got these guys, I've got these guys, I've got this, I've got these guys, right? So I've got a bunch of stuff in A complement too. A complement, it's going to be negative infinity up until 0. Oh, yeah. And then I get to union. Between 0 and 1, I want to include the irrationals. So I'll take the rationals complement and intersect them with 0, 1. That'd give me the irrationals between 0 and 1. What else do I have? I have everything between 1 and 3, but not 2. So I've got 1 to 2, 2 to 3, and then I've got 4 and things that are bigger than 5. So the complement of A is kind of a mess. Okay. But these are different sets. A itself was 0, 1 intersect Q. Closed 0, 1 intersect Q. Union 2 union the 3 to 4 union 4 to 5, right? So closure added some points, complement did the other things. What I want you guys to think about is what would repeatedly doing complements and closures do? Well, if I do the closure again, this already contains all of its limit points, so it's not going to get any bigger. But if I do the complement of this, so A closure complement, what's that going to do? Well, it's going to take the complement of this, so I go negative infinity up until 0. I go from 1 until 2. I get 2 until 3. And I get 5 off to infinity, right? So I've got more stuff, not as much stuff as A complement itself, because I took away the complement of the limit points too. If you repeatedly do this, how many different sets can you get? From taking complements and closures. The answer is 14. Let's see if you can find them all. That'll be a good exercise to make sure you understand what interior complements closures are. The other part of that, I guess. What is the interior of A in terms of complements and closures? we'll write that as A with a little circle there. That would be A interior. So let's just do that real quick. So let me draw A again. A was 0, 1. We've got all the rationals in between there. We had the point 2, and we had the 2 open intervals from 3 to 4 and 4 to 5. Okay, so the interior here, which are the points that I can draw a circle around them and stay entirely inside the set? A interior. A interior. Well, if I draw a point in here and draw a circle around it, part of it's outside the set, right? Any irrational number in that circle isn't gonna work for us. So none of these guys. This isn't entirely, no matter what circle I draw there, it's not going to be inside that. But this is going to be just the numbers between 3 and 4 and 4 and 5. How can I get just those numbers from complements and closures? Well, let's think about how limit points work. So the interior is everything inside. The limit points are kind of the stuff that's inside and the boundary stuff, right? So let's look at a complement. That's all the stuff outside. So if I take away the stuff outside and I take away the limits of the stuff outside, I should just be left with the inside stuff originally. So let's take a complement and then close it and take the complement again. Okay. So first we'll take the complement, look at outside stuff, and then let's take the closure of that, then include the boundary, and then finally look at the opposite. Okay, what that does, it takes away the boundary stuff and it takes away the outside stuff, so I should just be left with the interior stuff. Okay, let's see if that works. So, here's A. It's 0, 1, intersect the rationals. We've got a union with the number 2, and a union with 3 to 4, and a union with 4 to 5. Okay, so I've got a bunch of unions, and I want to take the complement of that. So we can use De Morgan's laws. Okay, so I should take the intersection of the complements of the pieces. Well, that's sort of hard to do, so we'll just go by the number line. The things that aren't in here, well, up negative infinity up until 1 are not in there. The numbers between 0 and 1 that are irrational are going to be in there. The stuff between 1 and 2 would be in the complement. The stuff between 2 and 3, including 3, would be in the complement. 4 would be in the complement. And the stuff 5 or bigger would be in the complement. Okay, now let's take the closure of that. So if I close this first interval, I get negative infinity up until 1. Union. If I close this stuff, I get from 1 all the way up from, this was a 0, wasn't it? And I get from 0 all the way up until 1. And then I include 1 to 2 and 2 to 3 is the closure of that part, and 4 and 5 to infinity, right? Okay, so I've got closed, 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 closed. I've got the finite union of closed sets, so that's going to be closed. Here's a complement, closure, complement, right? So I want the complement of all this stuff. So this actually goes from negative infinity to 0 to 1, negative infinity up to 0, up to 1, up to 2, up to 3. Okay, so that goes all the way from negative infinity up to 3. So I don't have any of that stuff in the complement, but I do have the stuff from 3 until 4, right? Because the stuff between 3 and 4 is not in the interval we've written down, nor is the stuff from 4 to 5. Other than that, 5 to infinity is in there, so this is a complement, closure, complement. Hey, that's the interior of A. Because none of these things are in the interior, this isn't in the interior, but both of these guys are. Okay. So that's another sort of exercise that you can try and do to understand these complements, closures, limit points, that type of thing, interiors and such.